Hello YouTube, welcome back to part 2 of the self-driving car series. I know it has been a very long time and I apologize for that, so I'm gonna jump right into it and get the main core mechanics out of the way. So this is where we left off last time with a car that had the acceleration and turning properties that go from -1 all the way up to 1. And we could also calculate the fitness. So a couple of mistakes that I made that I haven't fixed up yet is first go ahead and add a mesh collider to this track walls. We actually need the mesh collider to check the raise against it, so let's just add the mesh collider, make sure that's up and running, and once we have done that, let's go into the code and we just need to make sure that we have debug.drawLines here, and we can just copy the same line. This is in the car controller, the input sensors, and just put this line here, a line from r.origin to the hit.point with the color red, and just put that in each raycast, and that's for the sensors that calculate the distance between the walls. And once you play this, you'll notice that the red lines show up between the walls, and you may notice a small mistake, and you'll notice that even though the rays are supposed to be pointing in different directions, forward plus right, forward and forward minus right, they only point in one direction. The problem is with the mesh. I think I really messed up on this mesh. If you guys want to go ahead and recreate this, you can. Even then, like, how it looks is messed up, but the problem is I think the floor is a bit higher on this mesh here, so just go ahead and increase the Y position of your car. Actually, no, you know what would be smarter to do? Just move this cube.1 under your course downwards, and it should look fine. Just move it down here, and you can see it aligns with the ground now, so we can just go out of play mode and fix that up. Just drop it down, and now you'll notice not only does it look a lot cleaner because of those missing faces. If we play it, we should have rays that actually hit the course, and that should, give us proper values that we can now put into the neural net. Alright guys, so before we actually code up the neural net, I just want to clear up some things about how we're actually going to go about creating it. So the first thing I'm going to say is that I'm not going to go really in detail about how neural nets work, because there are plenty of videos that explain this and can explain it a lot better than I can. So I'm just going to show you what we're going to be using the neural net for, and how the genetic algorithm is going to train this neural net in the next video. So if you don't know the basics of this structure, then I'll leave some links down in the description, and you can go check that out and then come back. So basically what we have now is our little car here, and we have 3 little sensors that come out in these different directions. So we can call each one of these sensors I1, I2, and I3 for our inputs. Now what we want is 2 different values that are going to be both our acceleration and our turning value. And we want this value to be in a range of 0 to 1, and we want this value to be in a range of -1 to 1. So -1 here is left, 1 is right, 0 is no acceleration, and 1 is going completely forward. So now we have defined our inputs and our outputs for our neural network. That's the first step that we need to do before we create a neural net. So now we know the end and the starting structure for our network. So here, let's just draw that up. So we have 2 neurons for our inputs, 3. So let me just come down here. So we have 3 neurons for our inputs, and we have 2 neurons for our outputs. So we can say O1 and O2, I1, I2, I3. Okay, so now that we've defined the inputs and the outputs, we need to know what happens in this middle space here. Okay, so this is where our hidden layers come into play, and when we're coding it, what we're going to do is we're going to allow you to have a variable amount of hidden layers and hidden neurons. So you can play with the number of layers and the number of neurons in each one. So you can have say hidden layer 1, hidden layer 2, and we can have as many neurons as we want. And what's going to happen is every neuron in the input layer is going to be connected to the first hidden layer, and then the hidden layers are going to be connected to each other, and then the final hidden layers are going to be connected to the outputs. And then this should give us some useful values that we can use to steer and accelerate our car. So firstly, what's going to happen is, say let's just define our structure. Say that we have only one hidden layer, and we're going to have, say, two neurons here, 1 and 2. We'll call this H1 and H2. Now what's going to happen is there's going to be connections between this. So like I've explained here, there'll be a connection between I1 and H2 and H1, and similarly between these two, and then here, and there we go. Now we have all these connections, and the basics of a neural net is that each one of these connections has a weight attached. So there'll be a weight, and there'll be a different weight for each connection. And what will happen is that we give in the inputs, and they get multiplied by the weight. So the value of H1 here, so we can calculate the value of H1 manually. We can say the value of H1 is going to be equal to I1 multiplied by the weight of I1 and H1, so we can just call this weight 1, plus I2 times weight 2 plus I3 times weight 3. And now this is the first thing. We have a summation of all of the weights, and this will equal H1. Now there's one extra value that you may have heard of. It's called the bias. So for each layer there's a bias value, and this is just a set value that is not affected by the inputs. So this value will be between -1 and 1, and this is like, say, when you have a function on a graph, your bias value is like your y-intercept. It doesn't actually get affected by the variables, it just moves the function up or down by a fixed amount. So this function, say with the bias of 1, would be somewhere like this. And this is helpful for things like that need fixing within the network that aren't directly affected by the inputs themselves. So this, the bias, and then the individual weights are what is trained by the genetic algorithm. So once we've added all of these, we just add a bias value to all of this. So we say plus bias for that layer, so bias 1. And now the final step is we take all of this and we do something called an activation function. So take all of this, we add up all the weights, multiply it, do all this, and add the bias, and then we do something called activating it. So right now what's happening is we're multiplying constant inputs, so just normal numbers by other normal numbers and getting another normal number. And what this is going to do is definitely going to give us a linear value, like a linear function. So if you think of our neural net as just a big function of equations, just repeating over and over again, this whole structure just gives you a function, given a bunch of inputs and get out a bunch of outputs. The problem with having these weights here, multiplying and giving them to other neurons, is that we're going to have this linear structure here, and we don't want that. So what we want is a more curved structure that we can use to fit try to minimize our error as best as possible. And a straight line isn't the most useful, because in certain situations there isn't a direct correlation between the inputs and the outputs. There isn't that linear correlation. So what we need is some type of non-linearity introduced into this. So in order to introduce this non-linearity, what we can use is these are popular terms, so sigmoid function, and this is just, it will take a value and it will squish that value. So that's what it's called, like we can just squish the value between 0 and 1. And as you can see, any real value, I'm pretty sure any number can be fit. When any real number goes into the sigmoid function, it will be put on a graph between 0 and 1. So any number you give, it will return a value between 0 and 1. And the awesome thing about this is it's not going to be linear, it's going to be on this curved type of graph, and this introduces the non-linearity. Now there's sigmoid, which is also popular, and there's also something called tan H, and we're also going to be using this within our car. So the tan H, instead of the sigmoid, what it does is it's able to bring the value from 1 to -1. And the thing with neural nets is it isn't this strict theoretical thing that you can that you have to use. So like a lot of papers will be like, oh, use a sigmoid function, but you got to figure out what's useful for your scenario. So for us, we need, like I defined here, that the turning value needs to be between -1 and 1, and the acceleration between 0 and 1. And in order to get the correct values, we need to use the sigmoid activation for the first output, for the acceleration, and we need to use the tan H for our turning value. Now once we have this hidden layer, what we're going to do is for every layer up to the final outputs, we're going to use the tan H activation so that we don't lose any of the data along the way. So I'm not 100% sure if this is actually the correct, theoretical concepts, but based on experimentation, this is what I've found to work. So what we're going to do is for each hidden layer, we're going to apply a tan H activation function to this. So we're going to do all of these operations, and then we're going to evaluate it with a tan H. And it should give us a number between -1 and 1. Okay, so now this is just for one hidden layer that we've done this all for. And now we need to repeat this for every single hidden layer. Okay, so we do the same thing for the hidden layer, and now we repeat the same thing for the output layer as well. So we do all of this, except instead of input 1, input 2, we just use hidden layer 1, hidden layer 2. Now, this is the basics of how the neural net works. So how do we make this really efficient in code? So this is where we introduce the concept of matrices. So let me just create a new document here. Alright, so now we need to represent our neural net class in a more efficient format so that we don't do this weird looping through and finding the value individually for every single value in the network. So in order to do this, we need to represent our neural net as matrices. So what we're going to do in our case, for example, let's just say, oh, whoops. Here we have our 3 input neurons. So we have I1, I2, I3, and we say we have only one hidden layer, and we call this L1, and we'll call this I for inputs, L1 for hidden layer 1, and let's say there are 2 hidden layers, H1, H2, and we have our 2 outputs just like before, O1, O2. Okay, so now we need to define these layers in their own matrices. So what we can do is we can create a matrix for the inputs, and we can say the amount of columns is 3 for the amount of inputs. 1, 2, 3. Here we go. So we'll say I1, I2, I3. This is our input matrix. Now we need a matrix for layer 1. So layer 1 we can say is equal to H1 and H2. So each of these have their own dimensions. So the dimensions for this is 1 by 3, and the dimensions for this is 1 by 2. Now the dimensions of a matrix are very important because we need to multiply them in a specific way so that we get matrices of a specific dimension so they match up. So now the goal here, what we're trying to do, is find a matrix within these two that is of a size so that when I is multiplied by the weight matrix, so we'll call this W1 for the weight matrix, it will equal to the same size as L1. So what we're doing is we're multiplying this entire matrix here, which is our I matrix, by the matrix in here, and this should result in a matrix of size L1. So how do we design a matrix so it results in a matrix of size L1? So this is where the matrix multiplication rules come in handy. So what matrix multiplication rules say is that matrix A multiplied by matrix B is only allowed when the amount of columns in matrix A is equal to the amount of rows in matrix B. So what we need to say here is our weight matrix, using this rule, so our weight 1, the amount of rows that this should have is equal to the amount of columns in matrix A. So we know the amount of columns in matrix A, which is the inputs. We know the amount of columns here should be, the amount of columns here is, 3. So the amount of rows in our weight matrix should be 3. Now how do we know the amount of columns that go here? So we can visualize this in a better way. So let's say we have our 3 rows. So we have 1, 2, 3 rows, and each one of this is I1. Let me get rid of these lines. So we have I1, I2, and I3. This is our representation of our weight matrix. And what are our weights? It's a connection, it's a strength between each input and each hidden neuron. So for each input here, we need a corresponding hidden neuron. So in order for this to be valid, what we need is H1 and H2. Right, so now we have a matrix defined size of the amount of columns in I1 in the input layer, and the amount of columns in the layer that we want to make it equal to. Right, so now we have defined that the number of columns in the first weight matrix should be equal to 2, because we want a corresponding weight for every single input and every single hidden layer. So there will be a weight here, and weight here, weight here, weight here, weight here, and weight here. So now the computer can understand this very easily. Say we want the weight between the I2 and H2, right? We just look it up right here, I2 and H2. Boom, this is our weight right here. And now using the matrix rules again, when we multiply, say we'll equal this to the weight matrix here. So this is equal to W1. So when we say I multiplied by W1, this will result in a matrix of size L1. So now this is very simple. Once we've done this, all we can say is I matrix multiplied by the W matrix is equal to the L1 matrix multiplied by the W2 matrix is equal to the output matrix. So what I've done here, this is weight matrix here, and this is the second weight matrix connecting these two, and then we have this very simple equation that we can just run through, and boom, we have our outputs. And now there are a couple extra things we do along the way, such as adding the biases, but that's very simple because each layer has its own bias value that we just add to the end of this. So once we've done the matrix multiplication, we just have to add the biases, and the very last thing we do is once we've done the actual multiplication, we just loop through each one of these each one of these values, and we do the activation function described before. Okay, so now we have properly defined how we're gonna how the neural net is gonna work, how we're gonna split up the neural net into a matrix data structure. Now the final very simple thing is actually how are we gonna train these networks. So I'm not gonna re-explain this in the next genetic algorithm video because I'm just gonna explain it here. So what we have is we have our 3 inputs like usual, 2 hidden layers, and 2 outputs. And the way that a neural net trains is through the modification of these weights and these biases. So we have bias here, and we have another bias here. So what we're gonna actually try to do is we're gonna tweak all of these little parameters, all of these little weights, until we can make a function such that whenever given these 3 inputs, we're given a correct output. So all we're doing is we're trying to modify these numbers here to try and give us the best possible output for the given input. Now, the way a genetic algorithm does this is first we create a population of, say, 200 networks. So we create 200 of these networks, and what we do is we give them completely random weights. Right, so we have no idea what these weights are. We just let the cars do their thing, and we have a population here of 200. Say we have a population of 200 neural nets. So we have just 200 neural nets, and they all do their own thing, and we run each one after the other. And what we do after each car runs, we assign the fitness to them. So you might have noticed in the last episode we had this thing called overall fitness. That just tells our genetic algorithm how well that car has done. And now what we do is, out of these 200 cars, we sort them from worst all the way to best. So we have the best up at the top here. Okay, so all of these are the best cars that have performed the best, and since they're completely random at the start, some of these, even the best ones, might be like complete trash. So now what we can do is we can do a bunch of things to this. So I'm just going to give you one example of what we can do. Is first we can say, alright, so take the top 20% of the networks. These ones have done really good, so their weights and biases must be somewhat close to what we actually want. Right, and we take these top 20% of networks, and what we're going to do is we're going to breed them. So we're going to combine all these top 20% of networks. So combine top 20% of networks until we have our initial population again. So we combine, say for example, we combine 40 networks over and over again until we have 200 networks. So how do we combine them? Alright, so what we do is, once we have picked the top 20, we randomly select two parents 200 times. So we say parent A, and we find a random network from the top 20%, and we also have parent B, and this is also a random network from the top 20%, and then we combine these two to create a child A and a child B. And the way this works is, all we do is we randomly go through the weights and biases of both the networks, and we just pick and choose which ones we want and which ones we don't want. And this is a completely random process. So what we can say is, alright, so I want all the weights from the connection from the input to the first in layer. I want all of these weights from parent A, and I want these weights from parent B. And that's it. We just combine these two and create child A, and then for child B we do the opposite. We just reverse these two for the two different parents, and boom, we have child B. And then we just add this back into the population, and we rerun the whole thing, and then we make these two children now are the parents, and then we pick the top 20% again, and we repeat this process over and over and over again until we filter out the worst networks, and then we over time converge to the best results. And the problem with genetic algorithms are that they're completely random. So sometimes you may never find the result because the starting population didn't have the genetics required to converge to a result that actually makes sense or works. So what we introduce is this little thing called mutation. So out of, say, this 200 population, we give each child that is created a small little chance, say 0.01% chance of getting mutated. And what a mutation does is we completely randomize all the weights and all the inputs, all the weights, of the network. So it doesn't take any of the parents' weights. And this is wrong, actually, from a academic standpoint. What we're supposed to do is we're supposed to bump up a individual weight a little bit up and down, but sometimes for a general case like this, that could take a very, very long time. So with this mutation, it allows for a little bit of randomness. So what we're hoping is, at one point, we randomly get a result that will allow us to breed and then get to a stage where the inputs are actually useful and yield useful outputs. So I hope this explanation of genetic algorithms and neural nets was useful to an extent. I haven't read very deeply, and there are heaps of other things to take into consideration when building this. But I will leave a lot of resources down in the description for you guys to read. But this is my overall understanding and how we're going to be implementing it. The genetic algorithm is actually going to come next episode. But without any further delay, let's actually get into coding the neural network. Okay, so now I'm in the NNet class that I've created in the project, and we're going to go ahead and code up some of the things we talked about in the explanation video before. So firstly, we have the 3 sensors, and this is going to be in the format like this. So sensor A is going to be here, sensor B, sensor C, and we're going to pass in these values. This is going in, and this is going into our hidden layer matrix here, and then coming out with a bunch of 2 output values, the acceleration and the turning value that we can use to control our actual network. And what I've done with this neural net class is I've allowed you to have a variable amount of hidden layers and a variable amount of hidden neurons in each layer. And what that allows us to do is give us direct control over these hyperparameters, and hopefully then we can optimize it to find the best amount of hidden layers and hidden neurons for both performance and accuracy, because both are quite important. So now let's go ahead and create some of the key variables that we will need. Before we do that, however, we need to import a couple things. Last episode, I made you install the MathNet library, and it should be in your plugins here. If you double click on that, you'll see the mathnet.net, and that is useful for the matrix algebra that we're going to be doing. So stuff like matrix multiplication, these guys have optimized it, so when we're doing it every frame, we don't see any performance drops. So using mathnet.numerics.linear algebra, and that's the only thing we'll need, and we'll also need to use system. Alright, cool. Now let's go ahead and say public matrix float input layer equals matrix float dot build dot dense 1.3. Alright, what's going on here, you ask? So you normally see the syntax new matrix instead in front of things like this when you do object declarations, but what we're actually doing here is giving our matrix class a dimensions, which is the number of rows and number of columns, and we're saying we want actually here, if we look at our parameters, we should say here 1 row and 3 columns is what we want our input layer to be, because we have 3 different inputs, which is our A sensor, B sensor, and C sensor. And .build.dense says create this matrix that has just 0, 0, 0 as the values inside the matrix, and this will return a matrix that we're giving back to the input layer. So this is just a helper function given by MathNet that allows making matrices easier for us. Let's create another list of matrices, actually, since we are making a variable amount of hidden layers. We want to give ourselves the control of how to do that. So let's just bring in this in. So exact same concept here, except this time we're not going to initialize it. We'll just do that inside one of our methods, because we don't know how many columns we want, because we haven't actually assigned that yet. So now let's make the output layer, and with a little bit of help, what you can do to this neural net class, you can change these things to be variables as well, and change the output layer to be variables, and then now you have basically a general purpose neural net class. So I've designed this to be very, very like modular, so you don't even need the genetic algorithm to be a part of this. You can just use the neural net class however you want. and you can do back propagation algorithms with it as well. So I've made this very robust, so you can use this however you want. So now we have the input, output, and hidden layers, and you might be wondering what else is there. And what we need now is weights. So like I've explained before, there are weights between each layer, and I'm going to create a list for this as well. So we don't know the size of the weights because we don't know the size of the hidden layers. So let's create this. I'm missing a name. So let's create that. And one other thing we need are the biases. So if you've when you declare a function, you always have the end intercept, like the y-intercept kind of thing is the bias that we're declaring here. It doesn't actually take into account any of the inputs. It's just a number that gets added to the final output, so it just offsets the function up and down, is my understanding. I'm not 100% sure with this kind of stuff. And let's also add a fitness variable so we can bring it in from the controller. Okay, now we need to create the first function, which is the initialize function. So initialize is we're going to set up the weights, set up the weights and the layers. Yeah, the hidden layer and the weights is what we're gonna set up, and the biases. Okay, so let's create this here. Public void initialize int hidden layer count and int hidden neuron count. All right. So we're taking in two parameters, and we're going to use this to modify the hidden layers, weights, and stuff, you know. All right, so let's go in here. And first, what we're going to do is, in case we're initializing, say at the end or in the middle of a program, we can just be sure and say input layer dot clear, hidden layers dot clear, output layer dot clear, and weights.clear, biases.clear. So what I'll probably do is I'll split the neural net video into one, and then the actual training of the neural net with using a genetic algorithm into another video, because it's really long. It's quite a complex task, taking in these neural nets and then training them, and it has a bunch of code and a bunch of explanations. So I'll probably do one of another explanation for a genetic algorithm like I've done for the neural net as well, so you guys can keep up and, you know, split it between videos so it's quite clear, and you can ask questions in the comments regarding that topic specifically. Okay, now what we need to do is we need to loop through the hidden layer count and create that many hidden layers using the hidden neuron count as the column count here. I believe that is what we do. Yes, I am correct. Now for this video, it would be very useful if you had a little bit of experience with matrix math. I didn't have any experience when I learned this stuff at the start. So literally there's a website called Math is Fun that explains how matrix multiplication works. It's slightly more complicated than just multiplying a bunch of numbers together. There are specific rules you have to abide by when multiplying matrices. So looking at that kind of stuff would be very useful to understand why we're doing certain things to matrices, such as transposing them and stuff like that, fancy words. I'll try explain it, or maybe I have already explained it in my explanation video, not too sure. I'm probably gonna create that after I record this. Okay, so let's go and go hidden layers. I need to write this correctly. +1, I++, just add 1 to make sure we actually get the amount of hidden layers that the user wants. And let's create, let's just call this F, I don't know why, placeholder, .build.dense, 1 hidden neuron count. Okay, so we make sure that the rows always remain 1 because they are individual layers, so like they're just layers of 1 neurons going down. So here it's just 1, and then this is our hidden neuron count variable going down, and then across is just 1 for all of them. Even the inputs are 1 across, and the outputs are 1 across, so we can just keep 1 constant. Let's go down, and now let's say hidden layers dot add f, and the reason why we're keeping it in a list is so that we can just loop through the list and multiply all the layers, so you know we have it all the hidden layers in one list that we can just loop through. Biases, we're gonna add a new bias list, and what I'm gonna do here is, since we've got system declared, what I can say is using random equals unity engine dot random. So we don't have to say unity engine dot random dot range. What we can say now is biases dot add random dot range between -1f and 1f, and there we go. It's as simple as that. And now it's time to create the weights. So stuff might get a little bit worse here, but basically, if I try to explain this in my last video, we're trying to connect the weights from the previous layer to the current layer. So everything will change slightly. So what will happen here is the weights are going to, so if we had 1, 2 here, 1, 2, 3 here, the amount of weights between the first layer and the first, so here's the input and this is the first hidden layer, the amount of weights, the weight matrix between here and the weight matrix between the second hidden layer is going to change because there's a different amount of neurons in each layer. So what we need to do is we need to segment this off. So we can say if I equals 1, and if I equals 1, this hidden layer is connected to the input layer. So we already know how many neurons are here, and we know now how many neurons are in this hidden layer, which is the hidden neuron count. So we can design the weight matrix to have the desired amount of rows and columns to fit between the two layers, and they need to have a certain amount of rows and columns so that each input and each hidden neuron can have a individual weight going between this. So there'll be heaps of weights, and there needs to be a weight matrix so that each input neuron has a weight connected to each hidden neuron. Hopefully that made a little bit of sense. Here we go. So let's try and create this. So this is input to h1. We can say that, and we can say matrix float dot build dot dense, and we're going to make it so that the amount of rows is 3 and the amount of columns is what we're going into. So what I've basically done here is what we have. Well, say for example we bring in this one. So the input has here, it would be I1, I2, I3, and let's say our hidden neuron count was 2, just to make it easier to draw it. The hidden neuron count matrix would be here, H1, H2, and what we've done is now we've created a matrix in the weight matrix like this. So we have had here, I'm not sure if this is the correct orientation, but I'm just trying to explain to you what we've basically done. This could be the other way around based on the way I've declared it. I'm not exactly sure how MathNet does it, but here now we can have a random value here, x, x, y, z, x, y, whatever. Now what we can see is, say we want to find the value, the weight corresponding to I1 going into H1, boom, you have the value here. I2 going into H2, boom, you have the value going here. Now that's very useful because now what we can do is we can just multiply this matrix here into this matrix, and and now what this allows us to do is, using matrix multiplication rules, this will output, this multiplication here should output in a matrix the size of the hidden the next hidden layer. And the reason why we design it specifically like this is to accommodate the multiplication. So what you can notice here, this is the multiplication rule, is that the number of columns that you're multiplying the matrix should, like the say you're multiplying matrix A and matrix B, right? Matrix A's number of columns has to equal matrix B's number of rows. So that's a weird matrix multiplication rule, and what that will result in is a matrix of the exact size that we need for this one. Hopefully I've explained this better in my explanation, or I would also have linked a bunch of resources explaining why this works. I'm pretty sure 3 Blue 1 Brown has a great video on this, one of my favorite YouTubers. But basically, matrix multiplication rules will ensure that this works. So we've designed the size specifically so that it, when multiplied, it will give a matrix of size equal to the next layer. So if we're multiplying input layer and the first hidden layer's weights, it will give us the matrix of size hidden layer 1. So then what we can do is we can multiply input layer and then the hidden layer, the weights going to hidden layer 1, and then we can say, here you go, hidden layer 1, these are your values now, because the multiplication yields in a matrix of that size. If I'm wrong, please comment down below. Maths is really not my strong suit, but you know, I try my best. So we can go ahead and add this to the weights. Input to H1, and that's our first weight, and we've especially designed this for the input, but all the other weights are much easier because they're just hidden layers to other hidden layers. And since we know that all hidden layers have the same hidden neuron count, we don't even have to worry about this little rule. We're making the rows equal to the last columns. It doesn't matter because it's the same dimensions anyway. So we can just say matrix float hidden to hidden equals matrix float dot build dot dense hidden neuron count. Yes, hidden neuron count, and then we can just say weights dot add hidden to hidden. Alright, now this should give us a nice little weight matrix, and we also are missing one more thing. This has given us all the weights from input to the first hidden and all the way from the last hidden -1 to the last hidden layer. Now the one weight matrix that we're missing is the output weight matrix. So we need to have a matrix from the last hidden layer to the output matrix. And now this is where the rule comes into play again. So we know the size of our output layer is 1 and 2. So here, this gives us our value for the number of columns for the weight matrix. So let's construct this. Float output weight equals new equals matrix float dot build dot dense hidden neuron count 2. Okay, so like before, the A matrix, where the A matrix is the hidden layer, and then the B matrix is the output layer. So the B matrix, we want the multiplication between the hidden layer and this output weight layer to equal the same size as our output layer here. So what we want to do is we want to have the size here as 2 and the size here as the hidden neuron count. So let's just go ahead and say weight.add output weight and biases.add, and we can add one more bias for this extra weights layer, and we can say random.range -1 to 1, and boom. Now we need to create a function called randomized weights. So this is gonna go through every weight layer, every thing, and just make sure that all the values are randomized at the start. So it's quite easy to do this. Let's just go randomize weights And what we're going to do is we're going to do 3 nested if loops. So this is quite simple. We're just going to go through each of the weights, and then we're going to go through each, if I can type, of the weights rows, and then inside each row we're going to go through each of the columns. And remember the, oh wait, I always make this mistake. Let's get rid of this. This is y++. Remember that the weights are not just one row and then X amount of columns. They actually have a bunch of rows and a bunch of columns. Now that we have these 3 nested for loops, you can just say weights I x y is equal to random.range -1f. There you go. Now we have a bunch of randomized weights. So now that we have the randomized weights, we have the input layer, hidden layer, output layer, weights, and biases, everything is fine. Now we just need a function to actually run the network. So here we go. Let's go public float run network. Let me explain that notation in a second. Float A, B, float C. And here we go. We have a function that runs the network, and we're just going to return 0, 0 for now. So what this notation actually is, it's pretty cool. It just allows you to return 2 things without creating a struct. I think it's allowed in the new C# version. When I saw the C# release notes, I was pretty excited about this, because usually you'd have to go like this. You'd have to go struct A, float A, B, float C, and then you'd return a struct A here, and that's just quite annoying every time you want to do that. So I'm glad they've added support for that. They added this quite a long time ago, but I'm finally happy to use it, you know. Alright, so what we need to do now is we need to do all the multiplication and actually processing the layers. So remember that the neural net by itself does not do any of the learning. It's just a data, you can think of it as a data structure, something that holds a bunch of data. And then we have learning models such as genetic algorithms, neuroevolution of like augmented topologies, which is like that's the cool stuff. And we have stuff like backprop, and then we use all these different methods for different reasons, and we just impose that on top of the neural network, and stuff just works, which is pretty cool. Machine learning is awesome. All right, so now what we're going to do is we're going to actually set the values of the input layers based on our given inputs here. So let's just say input layer 0, 0 equals A, input layer 0, 1 equals B, input layer 0, 2 equals C. We're just setting the values of the matrices, and yeah, that's pretty cool. They have index notation for MathNet. So yeah, you can just set it like this. Now let's say input layer equals input layer dot pointwise tan h. All right, so this is where we have to explain it. Hopefully I did explain this, but if I didn't, you guys might have heard of the sigmoid function if you've done any reading into neural nets. Let's go here. Your sigmoid function, I believe, takes a value and gives you a value between 0 and 1. Pointwise tan, on the other hand, is between -1 and 1, I think. And 0 should be here. And the reason why we're doing this with a pointwise tan instead of a sigmoid function is because our values that we want at the end want to be between -1 and 1, because we've coded it here so that our acceleration and turning can be between -1 and 1. So we want to make sure that we don't lose any data throughout that allows our ability, allows our ability to get a -1 to 1 value. Hopefully I'm making sense. If we use a sigmoid all throughout, then by the end we won't have the possibility of getting a negative value. I'm not sure if that's 100% mathematically correct, but this has worked for me so far, and it comes inbuilt, so we don't actually have to do any annoying matrix stuff. So what we're going to do for our acceleration value is we're going to use a sigmoid at the very end. We're going to use a sigmoid value, but for our turning value, it can be -1 or 1, so we'll use a tan h function for that. But we don't want to lose any of the data throughout the propagation of the data. So we're going to use pointwise tan h as our activation function throughout. And the activation function is just basically to create non-linearity within the neural net, so it's just not this linear function, and we can actually modify it to suit our to minimize our error. Hopefully that is a correct explanation. Please go ahead and correct me in the comments, always willing to learn. So the first thing we need to do is we need to create the value for the first hidden layer. So first hidden layer is the connection between the input layer, so it's the input layer multiplied by the first weights plus the first biases, and that equals the hidden layer, the first hidden layer. And we got to do this manually because we have predefined matrices here, but for the rest of the hidden layers we'll just use a for loop and just get it over with. So here we go, input layer multiplied by the first weights plus the first biases and dot pointwise tan all of it, tan h. So what we're doing here, taking the input layer, multiplying it by the weights, and adding the biases. And if any of these have the wrong dimensions, our debugger will tell us, this is wrong, we're not allowed to do this, so that's good. So we're setting the value of the first hidden layer, and we're making sure to activate it using pointwise tan h. Now what we're going to do is we're just going to loop through all the hidden layers and just see what happens. We're going to say I equal to 1 because we don't want to hit hidden layers 0, because we've already set that. I minus hidden layers dot count I plus plus, and what we're going to say here is hidden layers I equals hidden layers I minus 1 multiplied weights I plus biases I dot pointwise tan h. So same principle as here, except we're multiplying the previous hidden layer by the weights connecting the previous hidden layer and this hidden layer, and adding the biases of this hidden layer, of the weights connecting these two layers, and then we're activating it. And once we've done that, we've basically completed all the propagation up to the last hidden layer. Even the last hidden layer has its correct values now. Now we just have to assign the values for the output layer. And this is quite a simple line. It's basically layer equals hidden layer, hidden layers dot count minus 1 multiplied by weights dot count minus 1 plus biases dot count minus 1, and guess what, pointwise tanning it all. What's the issue? Pointwise tan h. All right, now we have a full output. What seems to be the problem? I have some type of extra bracket somewhere. Oh no, it was right before. Okay, so taking the last hidden layer, multiplying by the last weight, and adding the last bias, and making sure to activate it. Now that's pretty much it. Now what we want to do is we want to return our correct values. So we're just going to return output layer 0 0 and output layer 0 1. Now, like I said before, we want to make sure one of these values is between 0 and 1, and make sure one of these values are between -1 and 1. Now to do this, we can again just activate it. So let's say this first output is acceleration and second output is steering. Okay, now what we can say is float math.tanh, and we can just take this in and pass it out. Because math.tanh returns a double for some reason, we can cast it to a float. Okay, so luckily our math library has that, and that's the reason, by the way, I imported system. You might have been wondering, like, why is this guy importing system here? This is why, because math has its own tanh. Wait, hold on, surely not. No, it doesn't have a tanh. That's cool. I don't know if they're the same thing. Actually, I don't know if they're the same thing, but that's okay. This works. Here we go. So we're doing math.tanh to this, but we need to do a sigmoid activation to this. There is no function out there to do a sigmoid activation. They should probably add that. So let's create our own. According to the Wikipedia definition, let's construct our own sigmoid function. So let's take in any float s, say, and let's return 1 divided by 1 plus mathf.exponential s. So this is just 1 over 1 plus e to the power of negative s. That's the function that's being evaluated here, and that should give that curve that I talked about. This is between 0 and 1. So let's just evaluate a sigmoid on this. And there we go. You have just created your first very own custom neural network from scratch. That's it. It was quite simple, and you know what? That's it. What we do have to do now is we need to go into our car controller, and we need to do a bunch of stuff to ensure that our network works. So let's go ahead, and first, before we do that, let Unity compile, and then we'll add a neural net class to our game object, and then we'll add a reference to it. First, before we do that, we actually need to get the reference. So let's go up here, and let's add a bunch of stuff that we need. First, we can say private nnet network, and we can use this get a component with it, and what we need is a bunch of network options, right? That's what we need. We need network options to allow you to play around with it and set the amount of hidden layers and hidden neurons. So here, layers, and these I'm just gonna put in some values that have worked for me. So 1 and 10 seem to work well. Actually, no, I'm lying. I haven't played around with this a lot. But I'll tell you later on what is a pretty good value for both of them, because I spent hours playing around with the layers and neurons, and why I'm allowing you to play with them. Like, what's the big deal? Like, more layers and more neurons does not equal smarter car. In fact, it can. It depends on the complexity of the course and the amount of, like, given enough training time, I'm sure in the end it might yield a good result. But the problem is, the more layers and more neurons you give it, actually I might be wrong about this as well, but what I've noticed is the more nuance it has a decision, right? The more time it takes to train, because it has way more parameters to tweak. The genetic algorithm has way more parameters to tweak, and since genetic algorithms are by nature random, this can take quite a long time. And even worse than a long time, the movement can be quite erratic and like quickly move from side to side without any, like, you know, flow, and it doesn't look that great. And that's because every small change in the sensor data is yielding in a much different output, and this is because there are way too many, like, you know, paths it's taking to reach the end, and even the slightest change on one end can cause a big change on the other end due to the random change in all these different parameters, all these different weights throughout the network. So, but I'm not saying lower layers and neurons are good either. You need to find that balance, because too low of these layers and neurons could result in, like, these inputs basically meaning way too much or way too little to a network. So you need to find the balance, and I'm sure I've heard that they created neural networks to optimize these hyperparameters. Not sure, that's a whole nother world of stuff, but let's first initialize our network and just say get component nnet, and this should obviously be on the thing, and let's just here require component type of nnet to make sure every time we add a car controller nnet appears. What else do we need to do? We need to actually initialize this, so let's do that. Since we do not have a genetic algorithm yet to do this, we can do this just as a test. So I'll just write some test code that we'll remove in the next episode. So I'm just gonna go ahead and go like this, network.initialize, and we're just gonna pass in hidden layer count. So that's neuron. Oh wait, no, that's layers and neurons. Here you go. And that should be all initialized. Now what we're gonna do is we're gonna go into the fixed update where we're doing this, and we have allowed for our neural network code to be here, and this is as simple as it's gonna get. We're just gonna say at equals network.run network, a sensor, b sensor, c sensor, and wow, that's it. You've got a neural net running. And let's go check this out. Actually, let me tell you how you can modify this to work with any problem. You have a custom neural network set up for any situation, so you can play around with this for any different like problem and just use the same neural net class. So just change this the amount of inputs that you want, make this a variable if you want later on, and you'll have to like initialize this by itself. You might add a bunch of parameters here like number of inputs, number of outputs, and you'd also go here and you'd change this from float to a list of floats, and also a list of floats here, and then you just loop through the list of floats and add them to the input layer, and then you'd just return the list of outputs. That should be very easy for you to change. So I'm giving you this neural net code. Whatever you do with it, it's free of use, have fun with it. Here you go. Now once we've done this, what's happening is our A and T is being controlled by the outputs here. So what's going to happen now when I actually run this, and once this compiles, which is going to take a while, what's going to happen is the input sensors are going to bring in values, and once it brings in values, we're basically going to assign random data to our weights, and it's going to evaluate the inputs randomly and give us a random acceleration and turning outputs. So this is going to be completely random behavior. So let's go ahead and add an nnet class here, and let's check this out. Let's just see what happens. Should give us some crazy random behavior. And it's not moving. Oh, here we go. Matrix dimensions error is always good. Let's check out what the issue is. Okay, quick digging around, and I found, I believe, what the issue is. So I'm going to go ahead and change one line, and I believe what I've done here, instead of writing hidden neuron count, I've written hidden layer count. So you see how even that like one little mistake can mess up all the multiplication. And you know what, it's great that MathNet directly interfaces with Unity, you know, tells us, you know, what matrix dimensions are, you know, messed up, and we can see even here it's telling us 1x5 is the first matrix that's trying to be multiplied, and then the second one is 10 and 10. So that's obviously not going to work. So once this compiles, let's go back in and change the layers to be 1 and 10 because that's what it was originally. I just played around with it before, and one thing I noticed is our Jeep box collider is off. Turn that on, or else there's no way to tell how we've actually failed the course. And let me play this. I haven't played this yet, so I don't know if this is right. Hopefully, please. Yes, there we go. Completely random motion. Don't know what's going on at all. And you can see that this is mostly just negative, and this is because our outputs are completely the same and we're not reinitializing. So let's just play around with this just a little bit more, and what we're gonna do is we'll just initialize it every time, so it just randomizes every single time it dies. So how do we do this? Where is our collision? Here we go. We have a little reset script. So in this, let's just copy this test code part as well, because this is well and truly test code. We're going to remove most of this in the next episode and convert this into a genetic algorithm. So let's play this now, and what should happen is every time it bumps against the wall, we're going to change up the weights of the network, and it should evaluate differently. And the reason why it was happening like that before is because it was getting the same inputs every time, and it was going through the same network each time, giving the same results each time. Alright, so now what we're doing is we're randomizing the weights each time, and you can see that there is variation. And you know what, once I've done this and the car has completed the course, I'm not even kidding, this has happened before. So now what's going to happen is when we're training, we're going to do a really hacky thing. We're going to go into edit, project settings, and what we're going to do is we're going to basically change the time scale, and our training is, oh my god, no way. That card just completed the course. And this is basically how the genetic algorithm works in the end when you think about it. All it's doing is running random neural nets and trying to find good ones. And look at this, with barely no help, our neural nets, some of them are just working fine. And this is testament to show that, you know, even like one layer, 10 neurons is completely fine. And also it shows that our acceleration and turn values are great. Like the sigmoid function works for the acceleration, and the turn value, the tan h function works. You know, the neural net isn't this set algorithm that you have to use for every problem. Look at this, it solved it. We don't even need training. Why even make a next episode? It's just solved it right now. That's amazing. I'm glad I have this on footage. This is a completely randomized neural net. But yeah, like a neural net is, you can modify it slightly to, you know, fit your problem, because a neural net is not about following set rules. It's about creating a structure that can solve the problem you're trying to solve. That's why there are things now like neuroevolution of augmented topologies, which is a really cool topic that I'm doing a paper on right now for my school. And once I completely understand how it works, I'm going to create another video with the exact same car, except with a much more complicated neural network structure. Basically, in this structure, the number of neurons and layers change throughout the program. So that's part of the evolution as well. You know how I was talking about finding the best amount of layers and neurons? Well, this network starts off with 0 hidden layers and 0 hidden neurons and evolves up from there. And I'll link the paper for this down below as well, because some of you might find it a very interesting read, and it is. And if you want a tutorial on that version as well, because I know there's a YouTube video from the same guy who this video is inspired off of, who made a neuroevolution of augmented topologies version of the same problem. So I'm more than happy to make a video on that. I'll just need a couple of months to understand it myself. But yeah, so I'm gonna wrap up this video. I apologize again for the very long wait, and I promise you the wait for the next genetic algorithm part of this video will be within the next 4 or 5 days for sure. So again, I apologize about that. And for those of you who are following along with my open world series as well, I've completed some of the major features such as the world streaming, so I'm going to be releasing that video in a couple of days as well. So thank you guys for watching this video. I hope you learnt about neural nets and all that fun stuff, and I'll see you guys in the next genetic algorithm video. See you next time, guys.